Hi, everybody. So my name is Jim Wander. I work in the platforms team at Google, and it's wonderful to be here. I just want to thank my hosts. This has been a terrific trip, and it's really wonderful to be here. And I'm going to keep the talk short. So platforms is responsible for delivering compute, storage, and networking infrastructure into our data centers. And this, I think, is the button. This is a slide. I'm not going to read it for people who want to know what this presentation is all about. So we have had a wonderful opportunity to build some very unique networks at Google. And aside from a management that really inspires and asks for and demands innovation, we had a couple other unique things I think that sets us up for these types of projects. First, Google had these large-scale data centers with very high networking demand. The applications they write are distributed, and it creates a lot of network traffic. We have a large staff of engineers that are good at writing distributed software at large scales. And the platforms team I'm in, the mission is all about investing in solutions that are optimized for Google's cases, use cases such as cost or power or scale. And so when I started, we were deploying traditional four-post, what we call four-post networking clusters, where top-of-rack switches would connect to 2 or 4 standard routers. This didn't scale, and the networking bandwidth and demands were going up exponentially, and the cost would be prohibitive. So we tried some experiments, and after a couple failed starts, we came up with multi-stage flow networks built out of merchant silicon with custom hardware. And over multiple generations, accumulating in our Jupyter project, Jupyter Network, which is a data center size flow network, we were able to meet the demand, the exponential growth, with a very high performance, large scale, and low cost networking. And we did this by keeping things simple and somewhere in the middle, adopting an SDN architecture. This is a picture of one of our data centers where you see racks of machines with rack switches on top. And all of our data centers today are using these SDN Jupyter networks. We also use it for our, what we call our B4. It's a bigger, better backbone network, but it's a wide area network, very large scale, high capacity that connects our data centers and allows for large scale data replication and data transfers between the data centers. All of this was built using a centralized SDN architecture. And what we see here is, this is a cluster network example where racks of machines are connected to a top-of-rack switch, which is little blue boxes, that all connect into an aggregation block, which is multiple stages of a fabric, and those are all tied together by a spine. And instead of having devices that are smart and run independent protocols, we have a central controller with a global view of the network state. The central controller, or big brain, as the attractive picture shows, is responsible for determining the routing and forwarding of all the packets, instead of the devices doing it on their own. And what the centralized control does is it lets us write the software, run it on Google servers, and we can do certain types of optimizations and control that would be very difficult with things like BGP. One example in our wide area network is that because we have central control, we can have a centralized traffic engineering process that is able to finely tune the load balancing of traffic between any 2 points. And so when the offered load on the network changes or the topology changes due to network failures, we can balance the load precisely matching the actual capacities. And that traffic engineering is very complicated, and centralized control makes it much more tractable for us to implement. And OpenFlow has been our foundation, our architecture that we've used all the way along with our SDN networks. Now, early on, we realized that OpenFlow was really good and worked really well on software switches. It was a bit harder to get working on our hardware switches. I mean, it works, and we've used it, but we had to customize it. We had to put in special extensions. We had to hack it up a little bit to exploit what the hardware chips offered. There was OpenFlow structure really wasn't perfectly matched with how the network ASICs were built. I think with things like TTP and multi-tables, OpenFlow has made progress, but it still has been somewhat of a challenge. We find every time we add an extension, my group, it takes a lot of time and effort, and we have to touch multiple pieces, so it's labor intensive. And with OpenFlow, every time there's an extension added or new feature to support, the protocol gets more and more complicated. So we're looking for something that works a little better. And so we've had a big success, but we've ended up in a state that doesn't really work well for us. So we have this, OpenFlow is not quite doing what we want. We've customized it, so now it's somewhat proprietary. So we cannot go out and buy either white box gear or traditional vendor gear and just drop it into our network. We have to do everything ourselves. And this is not where we want to be at all. This reduces the velocity that we can move and reduces the innovation that we can do in our networks. If you have to do everything yourself, that's not a great place to be. And what we really want is to be able to use the best of breed hardware, best of breed systems, whatever's available, and easily drop it into our networks. That's hard. That's hard to do. And so what we did is we teamed up with Barefoot Networks and came up with a new protocol, P4 runtime. It's a little confusing because P4 runtime doesn't necessarily mean you're using P4, but I'll tell you about that. We use it as a OpenFlow 2.0, it's a protocol to program ASICs from some type of software agent. Our use case is fixed function chips. Obviously, P4 was designed to solve the problem of programmable chips. Most of the chips we use are fixed function, and P4 runtime is actually designed for us to program fixed function chips. So if you're not using a chip that supports P4 runtime, we think, is still a good solution. What here P4 means is we're using the P4 language to define an interface. So we define an abstract interface into a device to program the chip with the P4 language, where OpenFlow has a complicated set of fields. The P4 language is built so you could do like a fabric.p4 or Tor, top of rack.p4, and that is the software, that is the interface the software is going to program to. We find that P4 gives, because of the way it was designed, an excellent representation of the actual capabilities of the hardware, and it's easy to extend, right? You just use the language to change the definition of the interface. So this abstraction, we believe, delivers us the ability to easily support multiple vendors in our network. Heterogeneous networks are hard, but if you have a consistent, stable API with P4 runtime, we think that will work well. And using P4 runtime also prepares for the future where more and more devices are going to be programmable. Brief description of what we have here is P4, our use case is centralized control. A lot of others use distributed control. In the distributed case, you might have, inside this blue box is a network device, and you might have local control agents such as BGP running on that device. And the BGP process could use P4 runtime to speak to the hardware programming layer. In our case, we have a centralized controller that will speak P4 runtime to every networking device, and the controller is programming, the software in the controller knows about this abstract interface, this ideal interface, and it's the same for all supported devices. It's the responsibility of the hardware-specific programming layer to map the virtual interface into whatever ASIC happens to be on this device, whether it be a Broadcom or a Barefoot or a Mellanox, et cetera. And because of the design of the P4 language, whatever capability of the hardware is there, we can represent in that interface. And so our one controller then can program multiple types of devices without change. Programming the forwarding and data plane is only half the job of using multi-vendor support. The other side is configuration and management. Google for a while has been promoting the OpenConfig standard. It's a declarative configuration model It has streaming telemetry for the effective and efficient collection of statistics and state. And we have specified 2 models that we'd like to see as a standard for use in Google networks. One of them is the GNMI, which is the Network Management Interface for configuration, and the other is GNOI for operations such as link testing and things like that. These are designed to be vendor neutral, so they would work with our own equipment and could be mapped onto any other vendor's equipment. And everything in there is we use it today, so it's all targeted for very practical, immediate needs. Instead of, it's not a standard looking for a use, it was a solution pushed into a standard. So, if we can get white box or traditional vendors implementing these 2 interfaces, our centralized controller and configuration system doesn't need to change and can support white boxes, multiple vendors, our own equipment, and that will let us leverage vendor capabilities and use the best hardware. Today is a big barrier to entry to putting something new. We think this will lower that barrier to entry, and we can quickly respond and use whatever the best solution is of the day. So, but a new standard is tough. That's a big job to come up with a new standard and drive it into industry. And so one of the things we thought would help would be to start an open source project. So we teamed up with the ONF to start a project that would produce a switch operating system that delivered P4 runtime control and OpenConfig. The ONF has done an amazing job of pulling together a team of contributors and a community of both vendors and operators. We'd like this to be, the aim is Stratum will run on white boxes. We'd also like it to support traditional vendors, right? This isn't a white box versus traditional business model. We want to use whatever's available and whatever is best fit. So we'd like, if a traditional vendor wants to use this code or maybe the test framework in Stratum, that would be great. There's also a lot of different switch operating systems out there now. There's Sonic, there's FBOSS, there's OpenSwitch. We don't want Stratum to be a competitor there. We'd like Stratum to be modular, and so if Sonic wants to use P4, we can get P4 into Sonic. We'd like Stratum to be able to help. So it's not a competitor. It's a minimal piece of software to support P4 runtime on open devices. Okay, and here's just an example of the teams we have from vendors and operators that are contributing today to the Stratum team. And thank you to the ONF for the slide. And this is, they've also built a nice community and pulled together a community of operators, software vendors, chip vendors, system vendors, and open source projects. Community's gone very well. And this is just a quick example of where Stratum is. So Google donated the code to get it started. The community's making progress. It's doing well, but it's a lot of work. And so you can see here the dots are yellow. Today it's in what we call a pioneering stage where the people who have access to it are willing to handle really messy conditions. By the end of the year, we're looking to open it up to the full project, targeting an open source release next year. And we're targeting some sort of lab trials next year in Google and perhaps at NTT. Stratum by itself is a nice technology, but a technology without an application isn't very useful. So I'm happy that it's it's an example piece of the UPAN reference design. UPAN is the Universal Programmable Automated Network, which is a data center network that is programmable and designed to support VNF applications. And I'm also happy that I guess SEBA or SEBA, I think it should be SEBA, could use, well, so we focused on data centers. It's also applicable to Access Edge, and where it could be, we're looking to make it part of a component that could be used in SEBA. And today, Volta uses OpenFlow. It could move to P4, and OpenConfig could be a very powerful way to manage the OLTs in the application. All right, so that was it. It was quick, but thank you for listening. And if any of this sounds interesting, we're looking to continue to increase the community around Stratum.
Thank you very much, Mr. Vanderer. Efendim çok teşekkür ediyoruz Sayın Jim Vanderer'a.